So, as Stuart says, I am very, very privileged to be the curator, actually, of the meteorite collection at the Natural History Museum. We do have one of the world's most significant collections of meteorites, and of course, about 70 million other things in the collection as well. But of course, the meteorites, as far as I'm concerned, are the most important specimens that the museum houses, and are some of the rarest and most precious of the samples, the 70 million samples that the museum houses. And hopefully in this brief talk, I'm going to give you a brief introduction about meteorites, what they are, where they come from, what happens when they land, where they come from in space, where they come from in time, and what we can learn about the solar system, and indeed how we got to where we are today from the study of meteorites. So this is an artist's impression of the sort of thing that would happen if an object about 10 kilometres wide were to impact the Earth. If you were in a spaceship or the TARDIS or something and you saw something like that, it would be pretty spectacular. Certainly if you were on the ground at the time, it would be spectacular for the instant before you were dead. So, I mean, really quite an amazing thing to happen. And of course we know that the Earth and indeed other planets in the solar system have been impacted by asteroids and comets in geological history. Of course, the most famous of these happened about 66 million years ago, and it was the impact that did for the dinosaurs and wiped out a lot of other species that were around at that time. But luckily for us, that happened, because if it didn't, we probably wouldn't have been here today, because this is where the rise of mammals came about after the Cretaceous Tertiary event, as it's known, about 66 million years ago. But the Earth is hit by smaller things as well. This is a very famous crater in the north of Arizona, near the city of Flagstaff. It's called the Barringer Crater, or Meteor Crater. And you can see very sort of distinctive hole in the ground. This really is your stereotype of what we term a simple crater. And this was formed about 49,500 years ago by the impact of an object that was about 50 metres wide, so probably about the size of this lecture theatre actually. And just to give you an idea of the scale of this hole in the ground, it's about 1,200 metres across and about 300 metres deep. So if you're ever in that part of America, going to the Grand Canyon or anything like that, I really would recommend that you go and have a look at this. It's a really spectacular natural thing to see. And this is just, I've actually been lucky enough to visit this crater a couple of times, and the picture on the left is called House Rock. The reason why it's called House Rock is because it's the size of the house. Like most geologists, we like to keep things simple and descriptive. And if I just flick back to the last image, House Rock is actually just around here, just on this limb of the crater. And from the rock type that House Rock is made from, we know that it came from right in the middle of the crater. So, you know, a very energetic impact to get a rock the size of a house, a rock the size of a house out and eject it from where it was. So really quite energetic impact. Now, we can actually work out how much energy is released in these impacts, and we can compare them to other things that we know are very energetic, for example, nuclear explosions. So this is just a simple graphic that I whizzed up after reading some papers about the energy released in the event that created Meteor Crater. And I've got a laser pointer. Or shall I just do pointing? I'll just do traditional pointing with my fingers. So here we have obviously the southeast of England. Here is Meteor Crater, to the right scale, right in Bermondsey in southeast London. I chose Bermondsey because that's where my boss is from. If you were in this area, in this red zone, probably the best place to be. When that impact happened in the red zone, you may be aware of a very bright flash, then you'd be incinerated. So, you really wouldn't know anything about it, to be fair. Yellow zone, not so good. You would probably have very severe burns on exposed areas of skin, but you wouldn't be actually in too much discomfort for too long, because when the shock wave hits you, all your internal organs will be pulverised and you'll be killed that way. So, and then if you're in the blue zone, Again, you may well suffer temporary blindness if you were looking in the direction of the flash. Again, on uncovered or unprotected skin, you would suffer something like a quite severe sunburn, but you would get over that. But even to the edge of that blue zone, when the shockwave hits, the wind speed is estimated at something like 140 miles an hour. So obviously lots of flying debris, things like that. So we know that the energy of the meteor crater event was the equivalent of an 11 megaton nuclear explosion. And there is actually a local extinction event recorded in that area in the geological past about 50,000 years ago when this thing hit. So we know that if it was something like that to happen today and land over a populated area, there would be huge numbers of fatalities. But we can actually calculate the frequency of these things, and this is quite a source of interest for us who study meteorites and meteors and things like this. I have to say I'm not an expert in this, but one of my colleagues does this sort of work, and you can see the sorts of frequencies that these things are expected to happen. Although there's a bit of arm waviness about it. We're talking statistics of small numbers, so it can be difficult. But something about the size of a meteor crater, we reckon, well, calculations show should happen about once every 1,000 years. That's probably actually too frequent. It's probably more likely one every, say, 10,000 to maybe 100,000 years. Something of the size of the KT impact, this Cretaceous tertiary impact, the one that did for the dinosaurs, that we reckon about every 100 million years or so. And then smaller things, an annual event of about 20 kilotons, we reckon, obviously, an annual event every year. And then Tunguska is a very famous event that happened in Siberia in 1908. We reckon that's something of that size about once a century. Now, this is quite interesting because we have obviously had quite a recent event, which I'll talk to you about in a little bit. But this is a fantastic document that I became aware of, which took about 8 months to get from the National Archives because they declassified it and then they lost it. So unlike us at the museum, they don't know where all of their stuff is. Of course, we know where every single specimen is in the museum. So I don't know whether you can read what this says, but it's a great document. In fact, it was done by the UK Atomic Energy Authority scientists. Estimated risk of multiple fatalities due to meteorite strikes on England and Great Britain. Brackets, England, Scotland and Wales. Okay, and here's it's not a very long page, it's only about 4 pages, and that was the sort of the graph of frequencies that they came up with. So I actually plotted this up on a risk scale, which you can download from the internet. And the chances calculated by the UK Atomic Energy Authority scientists in the 1980s, or 70s whenever it was published, was about 1 in 7,000. Okay, so about every 7,000 years, one person in the UK should be killed by a meteorite. You've got that, which is obviously less likely of them dying of heart disease, but it's actually more likely than dying of fire, apparently. And you can see there storm, lightning, winning the lottery, bee wasp stream. This one here, this other meteorite, this is actually being killed in a large impact. Now, nobody that we know of has ever been killed by being hit on the head by a meteorite. Although a couple of people have been hit, we don't know we don't know of any deaths, luckily. But maybe one person every 7,000 years in the UK will die, according to the statistics. But as I said, the statistics are small numbers, so we're not entirely sure. Now, obviously meteorites are landing on Earth all the time. We calculate that 40 to 60,000 tonnes of material hits the Earth every year. Most of that's in the form of very tiny dust grains that you wouldn't even notice. But obviously, every so often we get larger objects falling, which subsequently land on Earth as meteorites. And this is a very famous video of the Peekskill fireball. And then there was a meteorite that landed from this. So 1992 this video was taken. You can see the spectacular fireball coming in, and it's just there. It looks like it's going behind the trees. So a really, really amazing video. So one of the things that I often get, in fact I had one this week, gentleman phoned me up saying that he'd seen a fireball in Scotland about 10 years ago, and he'd seen the fireball and he knew exactly where the meteorite was because he'd seen the fireballs were coming down. It was, I won't bother explaining, he went into great detail to me to tell me exactly where he knew, how he knew that it had fallen and where it had fallen. So this is a picture obviously of the northeast of the United States. That video was taken here, in the town of Salzburg. The meteorite actually landed here, in Peekskill, which is in New York State. So the scale there is about 500 kilometres away. So if you are ever lucky enough to see a fireball, nothing's going to land anywhere near you. Okay? This is something that's happening high up in the atmosphere. You're seeing something high up and something that's going very, very quickly. So if a meteorite does land, it will not land anywhere near you, unfortunately, but maybe fortunately, maybe you would be 1 in 7,000 that gets killed. And this is what happens, this is what happened when this meteorite actually landed. It landed on the boot of this car, and it actually went all the way through the boot of the car and embedded itself in the decking that the car was parked on underneath. Now this is not the owner of the car, this lady, this is the owner's mother. She's looking quite pleased with herself because this car, which was really just it was actually a daughter's car. It was just a sort of old banger. They actually sold this car for, I think it was $100,000 or $150,000 to a meteorite collector. So if your car is ever hit by a meteorite, or indeed any of your property is hit by a meteorite, consider donating it to the Natural History Museum. But we would reward you. We would reward you with a bit of money and the knowledge that you've done a good thing for the nation, but you could make quite a lot of money. So she was quite pleased with herself, although the car was a write-off. So this is the video I want to show you now. I'm sure you've probably seen this. So this is a video of the Chelyabinsk fireball, which happened on the 15th of February earlier this year. And this is one of my favourite videos. So this guy's just driving to work, and here it comes. Absolutely spectacular. Now, do you remember the graph I showed? It showed the frequency, and there was something about the Tunguska size has happened calculated up about every 100 years. Well, this video, or the video of this fireball, this was a Tunguska size event, and it happened in 2013. Tunguska happened in 1908. So 105 years, okay, still pretty close to 100 years. So this Chelyabinsk event really is unique in terms of that we've never recorded anything of this scale before with videos and things like that. And there was huge amounts of videos taken. Now we've got sound for this one, so please excuse buzzing. Now, does anyone speak Russian? Fluently? Right, okay. Well, please excuse the language. I don't speak Russian, but a colleague of mine does and says, ooh, that's like the worst rude word. Although he could be a little money, I don't know. But anyway, so yes, these are, oops, wrong video.
Я сейчас поведу, подожди.
So that loud crash is the shock wave hitting. Can you hear the booms?
Ебать!
There's one.
Волоса накрыло!
The thuds
Да волоса накрыло, смотри!
are actually sonic booms from individual fragments of this explosion, of this meteorite. So what actually happened here was that, I'll just play it.
Я сейчас поведу, подожди.
Play it again. Everybody's gone outside, they've seen this flash, they've seen the fireball, they've all gone outside to go and see what's going on, taking videos, taking photographs, and about 2.5 minutes later, a shockwave of the explosion actually hit. And that's why so many people were actually injured by flying glass. You can see the windows here have all smashed in. About 1,500
Малоша, красиво.
medical attention.
Да, малоша, крыло, смотри.
Thank you, Russians. Right. So this thing exploded about 22 kilometres up in the atmosphere, and we saw that in the video of the fireball, that very bright flash. That was this thing literally exploding itself to bits. And the calculated energy of that explosion was about 440 kilotons. So again, a pretty significant size explosion, something equivalent to a fairly reasonable size nuclear explosion. And because this thing obliterated itself, more or less, this is the sort of size of the fragments that were being found. This is about the size of at the end of one of your fingers, about a centimetre across. And in fact, up until a couple of weeks ago, the largest fragments from this meteorite that were found were about 2 kilograms. But actually, last week, or the week before last, they did manage to actually recover this large fragment from the lake. So you may have seen on the news about them pulling this out, and when the meteorite fell, the fishermen reported that there was a hole in the lake, so they thought that one of the pieces had got in the hole, and then they couldn't find anything, so they thought maybe the fishermen were lying and being dynamiting fish. That was something one of my Russian colleagues told me. And anyway, they did actually find a fragment of the meteorite in the bottom of the lake, actually buried in sediments at the bottom of the lake. And this thing's about 630 kilograms, we think. So pretty sizable chunk of meteorite, but by no means the largest meteorite that's ever landed on Earth. So prior to the late 1960s, there was only about 2,000 known meteorites. And at that time, the museum had over half of the 2,000 known meteorites. And of those about 2,000, about 40% were ones that people had actually seen to fall and then had been recovered. As of a few days ago, when I last checked the database, we've now got nearly 47,000 known meteorites, plus about another 11,000 which are in the classification process. So they are meteorites, but they're not officially classified as meteorites yet. And of these, there's only about 1,100 which are witnessed falls. So now the statistics are saying that it's about 2.5% of all meteorites we know about are ones that have been seen to fall. We get a lot from northwest Africa. Look at that, nearly 31,500 meteorites from Antarctica. Now, the reason that we go to places like northwest Africa and Antarctica is these are deserts, and these are very good places to look for meteorites. So, here we have some pictures of Antarctica. This is the Frontier mountain range in Antarctica. This is a region of Antarctica which has been very fruitful for finding meteorites. And all the little red dots there on the map on the right-hand side are showing where meteorites larger than about 50 grams have been found in this area. And one of the reasons that you go to Antarctica is that not only are the meteorites well preserved, because it's dry and cold, helps preserve the meteorites, obviously they're easy to spot. So you can see in the image on the left-hand side, there is the Frontier mountain. It's granite rock, so it's quite light in colour. And you can see, here's a scientist collecting one of the meteorites, dark rock in amongst all of this light rock. So they're very easy to spot. So that's one of the reasons why we go to Antarctica. But also as well, Antarctica has environmental factors that help actually with collecting meteorites. So what happens is the meteorite lands on Antarctica, it gets caught up in the ice, and just as with rivers on the continent, the glacial ice in Antarctica flows from the centre of the continent out to the edges of the continent, trying to get to the seas. And what happens is that the meteorites caught up in this ice slowly move along as the ice moves along, locked up in the ice, protected from the elements, and then that ice comes across a barrier, one of these mountains, part of the Transantarctic mountain range. And obviously ice can't get through mountains, a lot can get through mountains. So the ice starts butting up against the mountain, and you have these very strong winds in Antarctica called the katabatic winds, and they actually scour the surface ice away. And so the meteorites actually end up working their ways to the top of the ice, onto what we call a stranding surface, and they actually collect and accumulate there. So not only are the meteorites being preserved for a long time because the ice is protecting them, They're easy to spot, and you've got natural mechanisms actually collecting them in one place for you. So it's a fantastic place to go and look for meteorites, and hence why there's been so many being discovered from Antarctica. Another good place is to go are hot deserts. I mentioned Northwest Africa. We go meteorite collecting in the Nullarbor plain, which is in the south of Western Australia and the west of South Australia, and you can see this beige sort of semicircular area here. This is the Nullarbor plain of Australia. It's a limestone desert, so very, very sort of flat. It's not completely free of vegetation, but it's vegetation poor. This is what it looks like. You can see very sort of desolate, really not a lot going on, with this sort of buff brown coloured background. Very, very easy to spot meteorites on. And then, oh, actually, I thought I had another slide there, but it seems to have taken it out. But that's one of the places that we go meteorite hunting. And in fact, on the last trip that we did to Australia, we were very lucky. We found the second meteorite from the moon ever to be found in Australia. So we were quite pleased with ourselves, although if there's time at the end, I'll tell you a story about that. So we've seen a little bit about where meteorites land on Earth, how we collect them, what can happen if big ones land. But, you know, why are meteorites important? Well, as I mentioned in the introduction, they're treasures. They are treasures, not like treasures, they are treasures. And they record so many different parts of the solar system's formation and then subsequent history. So this is, I'm afraid it's a bit pixelated, but this is a video which is an artist's impression of a star-forming region actually in the Orion Nebula. And all of these little sort of fuzzy blobs are stars with disks of gas and dust surrounding them. When we strip away all of this sort of energy that's blocking our view, what we would see is a young star jetting through its poles, being surrounded by this swirling disk of gas and dust, what we term a protoplanetary disk. And many of the meteorites that we have in the collections, and there's a great area of research, both for scientists at the museum and around the world, is looking at the different components within these meteorites and actually seeing, they're like little time capsules, letting us look back at the geological history of what was going on in this protoplanetary disk. So really the building blocks of the planets that currently are in the solar system. So this is going back to 4.6 billion years, give or take. And this is a picture of one of these meteorites. It's called a Carbonaceouschondrite, and this is a false colour X-ray map. And what you can see, hopefully, at the top, there's a very, very large object, which is a sort of yellowy, whitey blue colour. There's another yellowy, whitey one to the right of it. These are called CAIs. It stands for calcium aluminium rich inclusion. And these are the first solid materials to form in that disk of gas and dust surrounding the young sun. So when we talk about the solar system being 4.5 billion years old, we can actually say it's 4,567 million years old. In fact, I think it's 4,567.3. The accuracy is getting much better. That's how we know, by actually looking at the formation ages of these objects called the CAIs. And it's a big area of research, and it's one to say I'm quite proud that the UK is actually pretty good at doing this. So we do this with colleagues down at the University of Bristol. We have other very interesting things in Carbonaceouschondrites. Sorry about this, it's a bit difficult, quite a difficult picture to take of this object, because actually this is on display in the museum, you can go and see it, so I have to take you through the glass of the display case. This is a meteorite called Carbonaceouschondrite. It fell in South Africa in 1838, and in front of it is a very, very scientific tube with some tinfoil shoved in the top. And this is not just some manky old tube, this is actually was an ultra clean tube, and I don't know if you can see in the bottom, there's a sort of grey streak. Now that's not just sort of dirt, that is actually thousands and thousands and thousands and thousands and thousands of what we call pre-solar grains. And in fact, these are pre-solar diamonds. These have been extracted from the Carbonaceouschondrite meteorite. You have to actually dissolve the meteorite up to get these things out of it. So this is an example of a very destructive process. And you get this residue of diamond left, where after you've attacked it with various types of acid. And these pre-solar diamonds are very interesting and give us a real insight into how our solar system formed. So if you have a look at the composition of these pre-solar diamonds and other pre-solar grains, you can actually see there are at least 6 different populations based on things like carbon and nitrogen and oxygen chemistry. Now what this actually means is that there were at least 6 different stellar sources providing material to the region of the galaxy where our solar system formed. At least 6 different populations of these grains have been identified. And just to show you on this graph, if you were to take anything from our solar system, so you take a piece of my hair or one of the chairs or a piece of grass, even a piece of Mars, a piece of the moon, everything, in terms of carbon and nitrogen, everything would plot right in the middle where these 2 dotted lines cross. They're plotting the solar composition range. So all of these dots around this graph, not plotting on the solar composition range, mean that these things could not form in our solar system. They did not form, they don't have the right chemistry. So as I said, we know that they must have formed in a region other than our solar system and in a different chemical environment. So we're actually recording, as I said, 6 different inputs from stellar sources that contributed the material to our solar system. And then we have a look at something like Martian meteorites. So we can look at chondrite meteorites. They tell us about the birth of our solar system and what was happening in the first few million years of our solar system starting, the building blocks of our planets. But obviously we have pieces of planets in the collections as well. And so Martian meteorites are some of my favourite meteorites. I'm very interested in them. And they're very, very important. Because although we have sent lots of robotic missions to Mars, and of course there's robotic missions going around today, we don't have any sample return material yet. No rockets have gone and picked up stuff and brought stuff back. So we have to rely on the Martian meteorites to be able to give us a real idea of the geology of Mars by studying these materials in labs. So people always say to me, how do you know that these meteorites are from Mars? Well, it's very, very simple. They have the chemistry of Mars written all the way through them. They have signs that show that they have to be from a planet. They are igneous rocks. They're very similar actually to some of the rocks that we have on Earth. And very critically, they have very young formation ages. So the asteroidal meteorites formed very, very early in the solar system. Martian meteorites formed much more recently. So that's one of the indicating things. But the clinching piece of evidence was finding within Martian meteorites trapped Martian atmosphere. And we know what Mars's atmosphere is made from because the Viking missions that went to Mars in 1976 recorded for the first time what Mars's atmosphere was made from, what the composition of Mars's atmosphere. And you can compare it with gases trapped in the Martian meteorites, and it's exactly the same. So that's how we know that these meteorites are actually from Mars. This is just a fantastic image to show you the sort of leaps and bounds of how we've actually come on with Martian exploration. And you can see here the little rover at the front is the Mars Sojourner, which visited Mars in 1997. Then we have the Mars exploration rovers on the left, and then this is Curiosity, the one that's going around doing its thing at the current time. So huge leap in technology each time a mission is sent to Mars. And then this little beast here is ExoMars. This is Europe's rover, which will be going to Mars, keep your fingers crossed please, in 2018. In fact, I'm working with the team making the eyes of this robot at the top there called the PanCam. So I mentioned, actually I'm just going to show you this video, I mentioned the non-destructive analysis of meteorites. So what we traditionally do is, if we want to see what's inside a meteorite, we have to chop it up, which of course is not particularly good. But what we've started recently doing at the museum is using CT scanning to actually see inside the meteorite. And this is a CT scan of one of the Martian meteorites that we have in the museum. Now, we've not actually chopped the meteorite up to make it square. We've virtually chopped it up just to make the images a bit more manageable. And what we've done is we've coloured in anywhere that has air, has space, is red. So you can see, hopefully, that there's red lines in here. These are just little cracks in the rock. And what we wanted to know was, did this meteorite have any gas bubbles in it, which might contain Martian atmosphere? Oops. Oh. You've just seen our very well-trained centipede there. Ooh. So just rotating, as I said, this is all done virtually. This meteorite is still intact. So you can see red on the outside there. That's the outside edge of the sample. And then what we'll do is we'll strip away the rock in a second, and there is one of these gas bubbles. Can you see? And I got very excited when I realised that this piece had a gas bubble in, and then I got very disappointed when I realised it's connected to the outside. So if there was any Martian atmosphere in there, it ain't there anymore. It's got distributed in Earth's atmosphere. So I've just looked at my watch. That is half an hour. I'm sure. Be quiet now. Thank you very much for your attention, and I don't know if there's time for questions, but I'm happy to answer the questions. Thank you.